session of our GYAN course on Introduction to Mathematical Finance. I welcome you, sir, again, and thank you for being with us. Thank you all the participants for being with us. Now, sir will start the lecture.
Yes, so the last lecture. So welcome back to this last lecture. So it will be on it now will be on artificial or machine learning methods in our introduction to machine learning. So you already had this lecture this morning, application of machine learning to option pricing problem. I indicated one way or one instance where machine learning is used. Let's say machine learning, it's a new fancy word just for nonlinear regressions like neural nets. And so this fitting of volatility surfaces is one area where AI methods are applied. This kind of, if you like, a model-free approach to fitting volatility surfaces. So I'm not really an expert in AI methods. I'm actually usually give lectures on mathematical foundation of artificial intelligence, meaning if you are interested to some extent why all these methods work, you have to go back to what's called statistical learning theory. That was actually developed in the 90s already, where more or less the mathematical foundation of the current revival of these methods were laid. That's basically approximation theorems, which tells you one of them is, for example, the universal approximation theorem by neural nets. This was under many other scholars by Hornig, who showed that every measurable function can be approximated by a neural net, a sequence of neural nets. So let me, computer doesn't work. Okay, let me see when I find it. So this short lecture will give you some indication where you find the some results on the underlying statistical properties. I show you in a minute. I show you more or less the structure of the lecture notes. Of course, only if we would have more time. Okay, so I have to log in again from my second device. Okay, like the mathematical foundation, usually it's called or the statistical learning theory. So the formal setting, you have, let's say, a classification problem or...
Sir, can you make it full screen?
Larger?
Can you make it full screen, your PDF? Now it's fine, sir.
Yeah. So statistical learning theory, this more or less tells you why this all works. And the typical example, okay, you have loss functions like expected error, or a typical loss function is also the misclassification error if it's a classification problem. And so all the fitting and the training. First, we have to find an optimal classifier. That's error minimization. And so if this would be a real lecture, would be done in fully blown, fully detailed in a binary classification. And what the people look mainly in is, of course, empirical classification. This means you don't have data. You only have data, no distributions. But this basically means you apply this theory to the empirical distribution. So the mathematical background of this, it's what's called concentration inequalities. Because of these approximations, if you think about it, like the central limit theorem are behind this, or law of large numbers, all these approximation theorems from statistics. And concentration inequalities actually tells you, like we all know, that if you have a sample of data, xn of omega are your data. You have n of this data, and this converges to the mean. That's why it converges. But what you are interested in data or whatever, AI you call it nowadays, but which is actually an interest anywhere. It's so how many data you need. Find n delta. So if you have enough data, and how many of these you need, that this is close to what you want to have. Let's say that's your classification, what you want to have, 0, 1, whatever this is. And so, of course, you don't want to deviate too much from this. Let's say you want to have an epsilon, and this should be smaller than delta. That's how much your approximation is concentrated about what you want to have. That's your objective. Well, of course, this is called the concentration inequalities. They have a much more fancy name in AI, somehow the probably most close estimator or whatever. There is this whole theory based on this, but if you call it concentration inequalities, nobody will look at it. So the AI guys, they have a much more fancy name. Does anybody know about this name? It's like PTAT or whatever. You know how this works. It's kind of marketing, but basically from a mathematical point, that's concentration inequality and Wapnick-Cherwonensky theory. This tells you how close to how, for example, you give 99.98% you want to be you want to have an error which is smaller than 10 to the power minus 4. Then these two tells you how many data you need. But imagine, even it's implemented everywhere nowadays. To understand why this is the case, you need to have some more quantitative tools, theorems, proofs, and stuff like this. And the second part of this lecture, today I will only give you a glance of this, is to apply this to neural networks. So it's also perceptrons is usually an old word for this. Linear discrimination is a big part of this one. Even in neural networks, you have many linear regressions, as you might know. You do a linear regression, and then you have the activation function. You do another linear regression, then you do the activation function. So it's a sequence of linear regressions, transferred into 0, 1s or classifications, or functions between 0 and 1, like probabilities. The activation function more or less gives you probabilities. And the activation function, like the thinking is, it will sense the signal or not. That the activation function might be like this, yes or no. Or it might be like this, is almost yes or almost no. Okay, and then a multi-layer perception. That's the one what's called nowadays. It's called the neural net. And this you can do what we have developed again in more generality. One can do for neural nets. So what we want to learn from data. We want to approximate a true function which relates input to output by data. This means we have input, like the pictures, which is a sequence of high-dimensional vector space. That's r to the power 1 million pixels. And each of the pixels is a grayscale. And you want to transfer this vector into typical example. I don't know what in your country is typical example. It's a cat or it's not a cat. Cat or not cat. Well, and you train it on many data. You have many pictures. Gray scale vector. Yeah, and you want to classify, okay, this picture is a cat or it's not a cat. No? I mean, that's it's learning, that's really boring learning. That's learning from many examples. Yeah. So learning in this case means we want to minimize the error rate. Yeah. And so the error rate, I mean, you just can say, okay, it's just probability, but you don't have to believe in probability theory, just misclassification, how often you do it. Of course, what you know is what basically you know is the joint behavior of the input and the output. And this is the how often a certain grayscale vector belong to a cat, and how how often a certain that's cat, let's say 0 or 1. This is two sets, and you have many pictures or grayscales. And then you say, okay, it's quite often it's 1, and sometimes it's 0. That's what you know, what you learn when your empirical distribution is like this. You just, if you like, you just take P already to be the empirical distribution of your training set. It just counts. I mean, you might think if you don't like probability, okay, that's what real is, but basically it really doesn't help you to consider the specific measure. So the reality, not the observation, but the reality behind the observation is actually a P. Philosophically, you might think, okay, there's only data and nothing behind it, which I don't believe. So there's something ground truth, as the AI people taught it, as a ground truth. That's actually a joint distribution of in and output. So an f will be a classification function. It's just a measurable function, and you say, okay, we want to have f of x equals y. And as close as possible at this one. But of course, we have a loss. If it's the loss function is the expectation, so on average, how often you do a misclassification. L of f of x, this is how distance, if you like, of your prediction, of your classification or prediction, however you call it. I mean, that's standard theory in statistics, yeah. But of course, even you assume there's a ground truth P, you don't know it. Yeah? What you want to have is a distribution-free upper bound. Yeah? You want to control the error independent of the ground truth of P, but it might depend on the data you have. And you see you want to have this error be small with high probability, yeah, based on the data. A typical distance choice, of course, is the L2. That's a mean square error, which appears everywhere in statistics, which is well known. And of course, you also know that this is related to conditional expectation. So theoretically, it's clear, if you want to analyze this, so the minimizer of this one, min of this one, f of x equals the expectation of y given x equals x. Well, that's the L2 distance minimizer is a conditional expectation. Expectation. This you should know. You should look up in a textbook. It's a conditional expectation. But this is clear. It's trivial or whatever you want to call it. And so that's why it's also in regression, you always have the regression function. But let's assume of course, in reality, we have examples like this. These are your data. X is and these are your observed data. We have now a discrete world. You say, okay, we have input 2, and we have these 4 outputs. Our training set consists on 4 different inputs, and like for input equal 2, we have these values of the output, and so on. Okay. And so if you have now a new 2, which of the 4 points you would assign? Which value? No, you have an observation of 5. Which of these 4 points you would assign to a value? Of course, the mean. You always assign the mean. Everybody would do it. It's very natural. And this is a conditional expectation. Equals y. And this is, you see, as a very nonlinear regression in this example. I cannot draw here. That's a problem. No. You have to open it in. I mean, everybody who has a little bit understanding of this, if you have now is 2, you would take 3. And if you have, let's say, non-observed ones, if you have, let's say, a function like And you would also extrapolate or interpolate. Now let's say you have a function, and then you have a value here, like you have 4. What would you take? You have to fit this function somehow. That's your fit. And then you would take this one to be the value of 4. Linear regression, this is what you learn everywhere. I would just say, okay, I take this one. But in many cases, of course, you don't have a linear function here. So that's why you can also say what we do is a non-linear regression, or it's fitting. So we want to estimate. This is equal this, not this function, but we had a different color here. I think it was this one. Here we want to figure out a function eta of x. And if in our case, which we will be a little bit more detailed, is this might be 0 or 1. As a classifier. Oh, no, sorry, that's wrong. We don't take this one. It's a conditional expectation. Our data in the classification are always 0s and 1s. It's even worse. In our data in the classification, you have some 1s, some 0s, so you have just frequency on 0 and 1. And it, of course, tells you the relative frequencies and the probabilities. Okay. So where's my... Okay, so we are back at the at this one, and we define just the error minimization that we want to have. This one. So this first part assumes that we get our optimal. This just proves that our optimal predictor is a conditional expectation. Yeah. Okay. Now we do binary classification. So this means y is now Bernoulli 0 and 1, and we want to. That's our optimal classification, optimal prediction, if you like. And how do we classify? We classify and say, okay, we classified. How would you classify if you know the conditional probability? This is 0 and 1. And if the conditional probability is larger than 1/2, then you put it in class 1. So it's also natural, and so this classifier is also optimal. That's called the base classifier. The base classifier classifies in class 1 if the probability to being in class 1 at point x is larger than 1/2. So, but do we also have optimality of this one? Yes, we have optimality of this one. you see, if we would have the eta of x, oh, this would work like this. Yeah, so the base classifier, it takes the optimal L2 predictor of the conditional expectation, of this Bernoulli random variable. And so if this is eta of x, you might, the problem is you might eta of x, you fit it here, and if it's larger than 1/2, then you specify it to be in class 1. So this one, that's kind of observed. You have some values observed. They have 0 and 1. This is always the observation. In the observation, you are either a cat, you are not a cat. You observed 0 and 1. Because, okay, you can say, okay, you have still, I mean, this is grayscale. You will not have, as we have done in the counting example, 1 million. It's a very, you will never have 2 pictures with the same grayscale. Now, this means in your data, usually, your empirical, let's put it, conditional expectation, you have some x where you don't observe nothing. You have some x where you observe 1, and you have other x where you have observed 0. So much are not in on the first step. It's kind of, it's not really what you want to have. So what you want to have actually is the red curve. And so this you want to fit. So in this case of binary classification, of course, our error will be different. Because that's a misclassification error. L of h, you have a classifier, h of x equals 0 or 1, depending on x, and y itself, it's 0 and 1. 0 and 1s. And h of x as well. No, that's your classification based on x, and y is a true. So if you calculate, that's actually the L1 error. In this specific case, L1 error. Now, if you calculate this, because it only takes 0s and 1s, so this will be 0 if they are equal, they will be 1 if they are unequal. So it's trivially, it's the L1 error. And we will see that our base classifier, our naive one, where we say, okay, we classify it to be 1 if the conditional expectation is larger 1/2, it's the best one. So that's what's called the base classifier. And you have here some formulas here. So any other one is larger, and you can actually, for any other classifier, you can actually calculate this for any other classifier. Sorry, this is the base classifier. You only unequal. You can the excess error. Okay. So what we have learned, despite this formula, we know even the best classifier will have an error. This is a minimal error. We have seen it's a minimal error because any other classifier is larger. That's a takeaway from this. So the minimal classification error as the base classifier. Okay, that's somehow first insight you should have if you do classification. Okay, what I cannot be better as the base classifier, which is based on the conditional expectation, namely I classify to be 1 if the conditional probability of being a 1 is larger half. Okay, that's nice, naive, good, and it's best. Okay. So, but we don't know the base classifier. So what we have to do is what's called empirical. We should base this on empirical. Okay, so we have some properties of the base classifier. We have formulas of this. An example here. We don't go through this. No, I mean, you can put it if you have densities. Your distribution of grayscale in class 1 has a density f1, and the grayscale distribution, the grayscales of non-cats have distribution f0. Or you can do it in any other. If it has density, your base classifier turns out to be this one. Density in class X is you would say likelihood. It's like a likelihood quotient you have here. And if it's larger than one half, you classify to 1. That's a likelihood times the population weight. There's also no surprise that like in any other area, in testing or whatever, similar formulas as well. Just to see you in the test, if it's normal distribution, you have even an explicit form of the base classifier if your input in the classes are normal distributed. Okay. But still, now you can do two things. In your data, if you have them, you calculate the densities of grayscale for cats and the distribution of grayscale. Of course, that's not feasible because in this case, in our picture, we of course Ex again is in R to the power number of pixels, which is quite high. And like you wouldn't assume that this has a normal distribution. You might, but I don't know whether you want to do that. That's not done like this. Just in other cases, you still have it. You don't have. Okay. So the empirical error, as I said, it just now you replace the probability measure you have, just the distribution on the data. Of course, if you think, okay, you just sampled from the underlying truth, you can also calculate the expectation. So this is the misclassification. We build HN based on this data, and then we assume again the true, which we don't know. HN is now you have kind of two randomness, put it like this, or two uncertainties. One is, okay, you first now if you believe your data was somehow not random, you build a classifier. So this is still a function of your data. But you, of course, don't know whether the next one will be also because if you have another data point, of course, you have different data set. So then you still assume, okay, there is some ground truth, and you take that. But then you have to average again a statistic theory. You do, okay, yesterday I have data, today I take a new data set, and I do it all the time. And if I do the same procedure all the time, I want to be correct with my approximation. So your data, of course, are also random, or are also changing over time. Or if you do it in India, you have different data than you do it in Europe or whatever. You have two sources of randomness. Still, also the excess error of having is never optimal, because that's the one which is the smallest error you can take. But you want to make it close to this one. Your classifier. Of course, it's reasonable in this context, where just our classifier, our optimal classifier stems from the conditional expectation of the posterior, the P. It's another name of this. It's a posterior probability. Posterior probability. Perhaps you've heard of this. You observe X, and then you have a probability that's in class 1. Posteriori. Posteriori probability. And posterior means nothing else as after. After observing X. Or after, I don't know. I mean, I don't know how you call it in AI. In statistics, it's just an observation. It's still not optimal, but now you want to find, okay, how many data HN you have. You need to make this small. You take, first you have to find your optimal. E.g. neural net based on n observations. That's what always done with this training. But still, you have to know how many data you need. So first you have to know how many data you need, and then you again do another approximation based on neural nets, which gives you in your neural nets the optimal one, for example. This will be also later. But the empirical risk classifier, that's the same as here. As I said, you just plug in the empirical distribution, and then this one is your empirical risk of a classifier H. Of course, the empirical risk is for any ground truth, P, the empirical risk in mean. If you have data set today, data set tomorrow, and so on, if you do the same HN each time, on average, you get the true risk of H. Since in our assumption, that's our assumption on data. Data means they're all drawn from the same ground truth. Now, of course, for given data sets, you always get an optimal one, which is defined here. If you have the data set, you classify as it's done on your data. That's always a classifier which is optimal because it does On your data, it's optimal. You see, that's the problem is it's overfitting, and it's extreme overfitting. If you have the data, you put it in the proper one. And if you don't have data, you just put it in 0. Then on your data, this is optimal. But does it help you? Not really. So you find always, on a given data set, you find always the best specifier in terms of the empirical distribution. This means if your criteria is just the empirical distribution, but sometimes the non-probabilistic people think, then you can always perfectly fit, but it's an overfit. Because you never know what your next data will be. Okay. Now it becomes more concrete. We take now a class of H. Because if we take all, we always find this one here. On your data set, it's always optimal. The empirical error given the data, this one is always optimal. So you have to restrict it to some set. Set of classifiers. Because we don't want to have this overfit. Okay, then we take in this class, which depends now on capital H, we want now to find the best one. That's what you do, as I said, for example, in neural net. You just take neural nets, and H is neural net of one specific architecture, and you just have to find the best parameter by gradient descent, backpropagation, whatever your favorite optimization procedure for the parameters is. And of course, as you know, the empirical error, the misclassification error is this function is not differentiable. So you actually on this one even you can do gradient descent. That's why you usually do gradient descent on the S2 error, even if you are interested in the L1 error, put it like this. But L1 is not differentiable. Okay, absolute value is not differentiable, and L2 square function is differentiable. That's all. You have to do what you know what you do, or you just do what everybody else does without knowing why. Okay. So, but this means your risk. Now, the empirical risk maximizer we only get if we can run iterations of backpropagation infinitely many. So you're always happy in real life, if you have an approximation, a good approximation of the empirical risk minimizer. Because the empirical risk minimizer, you need infinitely many times. So you say, okay, after 10,000 iteration, I had my epsilon, and I say, okay, that's a little bit higher potentially at the optimal error I can have over my class. But nevertheless, we now assume we have a classifier which minimizes empirical risk. But saying this, we always are happy in real life with H, I don't know, dash instead of H bar. But let's assume H bar equal. We negligent this we don't care about this epsilon. But in real life, you have also this epsilon. Okay. Such an A bar Yeah, H bar is called the oracle. Actually, that's just a belief that it exists, but that the technique will never calculate it in reality. So, so we assume that this oracle one, that's the best minimizer of the true risk. We have now, you see, true risk. Here we have empirical risk. Then we have true risk. And we have the oracle one, and we are satisfied with somebody who has a true risk which is close to the best specifier. And that's what we finally want. But we have this name here. We want to have an H check such that this is the true risk of this one is close to the best one. That's a deviation which might depend on the class where we have find the best one. H are all in this class H, and the probability should be this should be small, and this also should be small as well. So, and as always in statistics, or not in statistics, but here we have our excess error of this H bar is always like the error which we get if we only restrict, that's the best in H. And that's how H approximates base. Estimation, because we are restricting our estimation, let's say, to neural nets. And the second one is, and we can only do it, let's say, to a finite neural nets. And so the approximation error tells, okay, this can be arbitrarily small, like in neural nets. If we approximate the conditional expectation by neural nets, we can make this error as small as we want, but we have to have a lot of neural nets. And this is then the estimation error, which gives me, okay, if I have now my H hat, which is close, depending on the data I have, my H bar, which is based on data, will give me an approximation of H. H check will give me an approximation of H. Okay, just to make it clear, we just assume we have a finite H, which in AI is called a finite dictionary, which sounds better. So we will see that we can actually bound this. So the true error minus can be so H, again, what we do H bar is our oracle, and H check, that's our best empirical. In H, that's the best theoretical, put it like this. In H, this we get by here within an application here, that's like neural net, like stochastic gradient descent, backpropagation. We get something which, as I said, close to H check. H check we also never get, but we get something which is very close. We are happy with this. Okay, and we can see, okay, we can bound the true risk of the empirical one, empirical best, theoretical best, And we can bound it actually by this one. That's empirical error and true error. And as I said, we want to have this small, this Wapnick lemma tells us, okay, we have to work on this one. And this should also be at the end independent of our ground truth, P. That's quite a challenge. But of course, as mathematicians, we like challenges. So we can, the Wapnick lemma. So then at the end, what you get out of this Wapnick, how it's the second Chernovsky theory, VC theory tells you that the empirical risk can be made arbitrarily small. Oh, no, that's not that VC theory. That's kind of finite. We are still in the finite case. We have n. Let me see, where do we... that's a single one. So n is the number of data and delta. We can this would show for every classifier. The single one, okay, if we have then finite, we have to put here in n. As I said before, I didn't just call the name, that's based on our concentration inequalities. That's concentration inequalities. That's more or less, because this is 1 over n, L hat n, there's always like 1 over n, and so that's like law of large number, that's like speed of law of large number. So this means if you want to have this small, like epsilon, we start with delta, let's say delta being 1%, so in 99% of our cases, we want to be close. This gives you a large number, so we have to divide by a large number of data in order. And then, for each classifier, we have this one. And if we have finitely many, we just have a larger number even here. Delta is small, so this becomes large. If delta becomes smaller, probability must become higher. We need more data. And still we have only a finite dictionary. This means we have 10 neural nets with fixed parameter, and we want to find the finite. Here you see the challenge, which is mathematically really interesting, to make this also working for larger age than just a finite set. And if we take now here, if we take now our best empirical, best ground truth one, we have an inequality like this. Now that's always positive. H is our best empirical in this class, and this is the best. We also find this one. So this means if we have only finitely, we are done. But of course, that's only for education. We get these concentration inequalities. As I said, we don't go into this one. So now comes this VC theory, which you might have heard in the context of machine learning and artificial intelligence. This actually gives you M, let's say before we had this M, the number of classifiers we want to optimize over. Now we take a family of classifiers H and we have to determine what's called the VC dimension. Of H. That's a dimension of function space, look it like this. And so especially this equals M if H equals M. No, I don't know, but at least if it's finite, we don't have to consider it, but it's a generalization of we just if it's finite, we don't need it, we just take M. This was our statement we had here. If it's finite, then Wapnick and they developed own theory for this complexity. It's called complexity. Sometimes it's called complexity theory. And it goes back to Wapnick in the 70s. You see? That's interesting to see, and it's nice for mathematician. Before you could actually apply it, because it just didn't have the computing power. All the mathematical foundation was already done in the 70s. Just by thinking about the problem, trying to prove some estimation and so on. And so the revival of theorem, of course, became, okay, here from the Wapnick chain of, okay, we really need so much and we don't have so much data for the calculation optimization. We even need so much runtime that we will never find a computer who can do it. It was, at this time, it was just theory. Okay, I don't go to the proofs here. I just want to give you the final result. Okay, so now here we have actually an infinite. We take the empirical risk of this one, and we look how it deviates from the, because it's still true, this inequality is still, that's what our final goal is, empirical minimizer compared to true minimizer in your class H. You can bound it by this one. Okay, if this is small, it's also small. That's why you consider this term. And you see this result, it's a little bit more complicated than just the one before, but it's the same. You start with a delta. You calculate the dimension, the VC dimension of A, which actually is the VC dimension of H. It's the same, just called differently, because to H we have basically H is the acceptance sets of H. To each classifier, you have a set where the classifiers say yes. So it's a set theoretical result, actually. Just for the notation you can take here. So I don't know. So this is basically independent of, for every P you have this. The V does not depend on P. That's as a probabilist or an old-fashioned probabilist, that's what's called a uniform large deviation result. Because we know for each fixed age, n tends to infinity, this goes to, then we take a soup, uniform in age, and p. That's really a very strong mathematical result. This goes back to the 70s, and this is now applied in any computer without most, I think, 99.9% of the users don't know why this works. But this comes from this statistical learning theory, VC theory, developed in the 70s, a little bit later. And this has to do, perhaps this you have seen like shattering, you have shatter coefficient, you see your decisions areas, you 0, 1 variables, and so this dimension is very well defined, and it's really suited to the classification problem here, but also to not only to binary classification, you can easily extend it to that's now the formulation, which is then, if you have a family of classifiers such that the VC dimension of the acceptance sets V A bar is finite, and then we need at least as many data at twice the VC dimension, and then the empirical risk minimizers H of H satisfies that the one you calculated actually. This, again, I say you do by stochastic gradient descent or backpropagation, whatever. That's the empirical minimizer. And it's close to the optimal. Let's say that's your error tolerance. And basically this one is your probably high probability. This means if you minimize, you take, in all cases, if you do it like this, you get the minimal one. Then in most cases, it's close, because this depends on the data. But in most of your data sets, that is close to the optimal one by this error, independent of your assumption on the distribution of x and y. As long as you see your x, your data actually are an IID sample, they're independent, the data, which I, in some examples, doubt. You see extension might be done by different samples, not independent samples, which are more realistic than assuming all your data are just independent from the same ground truth. Okay. You see that's what we want. And if you want to understand this, I give you a book where you can read this, my favorite book on this one. This one. So I tell you, I give classes on this, on mathematical foundation of artificial intelligence. There come all these data science people, and some of them actually ask me, where can I all read this? And I tell you, read this book from '96. If you have a mathematical approach to problems, then you find everything here. Now you have to look a while because you see, I don't know how you see how many pages this is. But it is thicker than any math finance book I know. There's only one math finance book which is as large as this one. That's the one by Shirayev. But most finance books, this is really a very nice book. As I said, for people interested in the really mathematical foundation of artificial intelligence. Okay, so let me just now do one more concrete example. We now base our classification on a neural net. We have now a decision rule. Okay, I mean, the motivation is if you have a linear regression, then of course this is your optimal one. In a linear regression, your decision is clear. But if you have so 1 bit of a neural net, it's optimal to do linear regression. And so your overall neural net, you know these pictures here. You just have many. So you iterate, you put in here the output of the layer before, of the layer before, and you put in the outputs there. So it's you put in the neural net. It's basically you put in some sigmoid, take a linear function, an affine function, sorry, affine function. You have another one, it's a final layer. You put in another linear function, and so on. And you start just a specific type of function. Linear function, A0, sigmoid functions, and so on. Or you make. Neural net is just a function which is kind of complex in the way you put in linear function into activation function. The result you put in again in a linear function. The result you put it again in a. That's why you always don't just do pictures like this. You start with the input. You do a linear function. You put the output in each node. You put the output into a sigmoid function. Kind of between 0 and 1. You can also take this one, which is actually 0 and 1. And then you put the output again. You make a linear regression with this, and this is here you get a linear output. That's all linear. So that's it. The single steps are like, I don't know whether you know it from regression, you have probit and logit regression, which are already the first step here, and then you add this. Okay. And so the powerful thing about this is, okay, it's somehow easy. I guess I never did programming, but easy to code because it's recursive. And also the nice property that's a universal approximation is that it's known, actually, put it like this, to really tell you that's always a revival of nice old mathematics. Already Kolmogorov proved that other types of networks of this type, they said every continuous function can be arbitrarily good approximated by stuff like this. These are just linear functions. Then you put a sigmoid functions on this. For example, the product can be written. You take the single coordinates, add them up, and then put them together. There's a specific structure. Here you have only function which depends on single ones, single entries, single features, as the data science guy would say. That's just J's feature number J. You take a function on this, which means you sum them up. You take again another function, and then you. And this type, the question which functions are dense. Of course, what everybody knows from textbook is that polynomials by the Stone-Weierstrass theorem are dense. And so it's just to say, okay, I can, here you can already see it. I mean, that's how you prove it. No? You know, somebody told you, or you believe it, or you prove it yourself. Yeah? Polynomials are dense in the space of continuous functions. Actually, continuous functions are dense in the space of measurable functions, so only you have to show that your specific function class you have is dense in the space of polynomials. Okay, but if you can even construct polynomials by these functions, then they are of course dense in the binomial, because the linear span or whatever of this is equals in the polynomials which are dense. That's how all these proofs works. Yeah, or the proof which you find in these books. Yeah, they are based at polynomials are dense. You have to approximate polynomials and so on. Hmm? Or I think here it's even Fourier. Sine and cosine are dense. You want to approximate sine and cosine by neural nets. So there's no surprises. These functions are dense. Okay. To finish this lecture, I show you one application in hedging. That's a paper by it's robust hedging. That's a paper by again wrong. Okay, I hate Adobe. That's a paper by Thorsten Schmidt. It's called also robust hedging, I guess.
Yes, sir. We can see your screen. Yeah.
Yeah. Lithier Bomat. And just a second.
Yes, sir. It's okay.
Just a second. I have to figure out the. Antje Pomat, Eva. He and Julian Sesta. It's called Robust Deep Hedging. That's the title. And I just give you here one page of this where you can see how this works. Yeah, you have here the same, you have this hedging problem. Hedging problem. That's your derivative. You have your hedging error. That's like in, that's the hedging error. Hedge error. That's your hedge error. And robust means you don't know the exact distribution. No? You also take, that's the hedging error if you know P, and then you want to minimize over P in a certain set. That's why it's called robust. It generalizes, let's say, the approach. You don't know which you have, and then you see, then you just can put here in here to solve this problem, which gives you the least wrong hedge over all potential models you have. You take this neural network and you run this algorithm, where you do your data are now generated according to your parameters, but the parameters are random. You see you have a discrete version of an SDE, that's affine process here. Affine, well, generalized affine process, a class of processes, and you take random, you select because you don't know which weights you have, which parameters you have. And then you get the optimal for each selection of parameters. You now select the optimal H in the neural net. H in this neural net. And some of this, of course, inspired by general mathematical theory or finance theory that you want to hedge. And you have model uncertainty. And then from this, you get the optimal hedge strategy, taking into account the uncertainty of the model itself. In each single model, of course, you have the optimal hedge strategy. But what happens if you don't know which hedge strategy you have, which model you have? That's called robust hedging, and that's one application of many other applications of machine learning in quantitative finance, that like this robust hedging or deep hedging. Deep hedging is the same one. You can, for example, take what some people do. You don't take any model, you just take the stock data you observe. In your batch here, batch is generated artificially, but you can also take observed data. And then you do the same. What would have been the best hedge in the data you were considering? Okay, so I stop here. And thank you very much for your participation. And so
thank you.
Hope next time
Sir,
I will
thank
be
you so
partner.
much for all your wonderful lectures. So thank you. Let us thank our foreign expert, Professor Ludger Obeck, for his wonderful lectures. Sir, we thank you very much for you have given us your valuable time. So now, sir, you may leave as you are leaving for